a special class of systems famous as LTI systems, meaning they are both linear and time invariant. So these two properties of the system lead to the famous convolution sum. How these two properties, linear and time invariance, they lead to the convolution sum is what we are going to try to understand. So what happens is that if you apply a certain input, okay, so we are talking of discrete time LTI system. So then for discrete time LTI system, if you are introducing any arbitrary sequence called x of n, the output for this discrete time LTI system y of n can always be expressed as a convolution sum. Now, to understand this operation, let's first try to visualize x of n as for any arbitrary sequence x of n. X of n can be expanded in terms of weighted impulse discrete time impulse sequence. Okay, so delta of n, if you recall, by definition, it only exists at n equal to 0. Okay, but it turns out that you can express x of n in terms of shifted impulses. Okay, only the shifted impulses. So the key idea in visualizing how a discrete time unit impulse can be constructed, can construct any discrete time signal, is to think of a discrete time signal as a sequence of individual impulses. Okay, so any sequence x of n can be expressed in terms of this individual impulse, discrete time impulse delta of n. So to see how this intuitive picture can be turned into a mathematical representation, let's consider the signal x of n depicted in figure 2.1a. So this figure is shown over here. Now you have an arbitrary sequence of any arbitrary length. So you see the length is over here is infinite. But there are 5 shifted impulses that you can see in this part B, C, D, E, and F. So what is happening is that you have this shifted impulses delta n plus 2, then there's delta n plus 1, delta of n minus 1, and n minus 2. And with this, there are weights. The weights is the weightage, okay, or it's the scaling of that discrete time impulse with the corresponding sample from x of n. For example, delta n plus 2, exists at n minus 2. Otherwise, it is 0. Okay, so that's what here you see. So the sample only exists at n minus 2, right? And the weighting, the weight or the amplitude associated with the sample is the value of the sample at x of n equal to at n equal to minus 2. Okay, so in a sense, at each impulse, for example, this is delta n plus 1, which exists at n equal to minus 1. The sample only exists at n equal to minus 1. Okay, so similarly over here, the sample is supposed to exist at n equal to 0 because there is delta n, and then the scaling is the corresponding scaling is x of 0. Okay, the amplitude is x of 0. So this is x of 0. Similarly, this is x of minus 1. So in a sense, what is happening is we are decomposing this sequence x of n in terms of the unit impulse sequence. Okay, where with each unit impulse sequence, the weights are the corresponding samples of x of n. So for example, the mathematical description is as such. For example, with delta n plus 1, you have x minus 1. Okay, so you can express this like this. So x minus 1 delta n plus 1 means that the sample x minus 1, which exists at n minus 1, otherwise it's 0, otherwise it's not existing anywhere. Okay, so that's the definition. Similarly, the sample from x of n at n equal to 0 is x of 0. So this becomes the weight of the impulse sequence at n equal to 0. Okay, similarly, the weight at n equal to 1, you can write it as x of 1 delta n minus 1. So in general, what is happening is we are decomposing the entire sequence. So you can write this x of n is the collection of all these shifted impulse sequences, so on and so forth. So what is happening is that you are decomposing x of n in terms of the shifted impulses, right? So this is x minus 3 delta n plus 3, then x minus 2 delta n plus 2. So these samples of x of n, they are forming the weights or the amplitudes of the impulses, the shifted impulses, right? I mean, so this x of n, for example, can be written in general for any discrete time sequence. X of n can be decomposed in terms of the unit impulse sequences. Okay, so if you expand this, for example, if you expand this, there are terms like x of n minus 3. If you start with minus 3, then sorry, delta of n minus 3, delta of n minus 3 multiplied by, you see, the summation is over k, so then the weight is x of minus 3. Okay, so the same thing is, I mean, the expansion is over here, but just for if you have to write few terms, plus then for k equal to minus 2, this is minus 2. You see how the samples of x of n, they form the weights of the shifted impulses. So this is n minus 2, and okay, I think this is, sorry, this is plus, this is n plus 2, right? Because the k is negative, so this becomes positive, and then plus dot 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 plus the last term, or if you have to write for x2, then this is x2 delta. This, since k becomes positive, now we have negative. This is n minus 2. The k is positive. Okay, then plus x of 3 delta of n minus 3, and this thing continues, okay, for the entire length of the sequence. So what it says is that for any value of n, only one of the terms on the right hand side of the above equation is non-zero, and the scaling associated with that term is precisely x of n. So the scalings that are associated are the samples from x of n, x minus 3, x minus 2, x2. But in order to define those samples, you have to write that in terms of the shifted impulses. I mean, so for a sample at x0, this is x0 delta of n. Okay, the sample at any n can be written as x of n or x of k. Okay, x of k delta of n minus k, where k can be a positive or a negative integer. Okay, when, of course, when n is integer, k has to be an integer, right? So you can write any sample of x of n at k in terms of the shifted impulse, right? And if you sum it up, then this is the entire sequence. If you sum it up from k equal to, call it minus infinity to plus infinity for a general infinite length sequence, then this thing is equal to x of n. Okay, this is x of n. For example, if you sum this up, this entire picture, you sum this up, you sum the part B, C, D, E, and F of this depiction, what you get back x of n. Okay, so this is the mathematical interpretation of x of n. I mean, this x of n is a decomposition in terms of shifted impulses, right? So you see over here minus 2, this you have this sample at minus 2, then this sample at minus 1 comes up. So you're summing this up, and then you obtain the sequence by summing all the 5 below shifted impulses with the corresponding weights, which are the samples of x of n. Okay. That's the idea. So any arbitrary sequence can be decomposed, any arbitrary discrete time sequence can be decomposed in terms of the shifted impulses, right? So this corresponds to representation of arbitrary sequence as a linear combination of shifted impulse, unit impulse delta n minus k, where the weights in this linear combination are x of k. Now, as an example, let's consider a unit step sequence. Okay, since we are saying that you can write or decompose mathematically any sequence in terms of discrete time impulses. So let's try to do the same for a unit sequence u of n, which is a unit step. So in this case, by the definition, u of k is 0 for k for the negative indices for k less than 0, and it is equal to 1 for k greater than or equal to 0. Now u of n can be written as, because u of n is like this, so it starts with 0, okay, then graphically it's like this, it's 1, 2, and all the weights are identically equal to unity. Okay, so the weights are 1, 1, 1, and then this thing continues, okay, and this is a discrete time index called as n. This is your sequence U of n, okay. Now this sequence can also be decomposed into impulses. I mean, you can write this as delta of n plus delta of n minus 1. You see all the weights with the impulses, with the shifted impulses, are first of all they're equal to 1, and then you have the sequence in terms of the shifted impulses, okay, and this thing continues. So this thing is going on because this is an infinite sequence, okay, but then you don't have anything below n equal to 0. Below n equal to 0, the sequence is 0. All right, that's the definition of U of n, okay, and this continues on the left side as well. All the samples are 0. So the above equation is called the shifting property of the discrete time unit impulse, because the sequence delta n minus k is non-zero only when k equal to n. Okay, so that the summation on the right hand side of the equation shifts through the sequence of the values xk and preserves only the value corresponding to k equal to n. So you see the sequence is only present at k equal to n. So over here k is equal to 1, okay, so you have this sample. For k equal to 2, you have this sample. So basically you are again decomposing a sequence which is unit step in terms of the delayed impulses, okay. Note that this summation limits, they change according to the definition or length or the extent of the sequence, okay. The extent of the sequence is the number of samples that it contains, right? All right, now let's try to see how we can use this interpretation in deriving the convolution sum, which represents the output of a LTI system. So we have the okay. So let's say again we have an LTI system to which an arbitrary input x of n is applied. But first of all, let's consider, since we know that the system is both linear and time invariant. So what I'm going to do is I'm going to apply a unit impulse sequence delta of n, okay, which exists only at n equal to 0. Otherwise it's 0, okay. And then whatever my response is, I mean, if I drive a system, a discrete time LTI system with unit impulse sequence, whatever my response is, I call this h of n, okay. So h of n by definition is my impulse response. That means the response towards the application of unit impulse. So h of n is the response to the unit impulse sequence, okay. Now what happens is that if I shift this impulse sequence by, let's say, if I apply a shifted impulse, if I shift this by a positive integer, let's say k, okay, then my output is supposed to be shifted by the same delay k, right? Why is that? Because the system is time invariant. This thing, I mean, you can invoke the property of time invariance to show this, that if my input is delayed by a certain number of samples, okay, then the output is supposed to be delayed by the same number of samples. This is by the principle of time invariance. If this was not the case, then it could be n comma k, but not n minus k. It could be something else, okay. Then it won't be a time invariant, it will be a time varying system. So because of time invariance, the number of samples by which the input is delayed, the output is delayed by the same number of samples, okay. So this is time invariance. Then what I do is I scale this. I scale my shifted impulse by, let's say, a scalar xk. Note that the time index is n, k is not the time index, okay. So k is just an integer. So x of k could be any number, okay. It could be a fraction, it could be a number, positive, negative, complex, it's not important, okay. But I have scaled my shifted impulse by a scalar x of k, okay. Then what happens at the output is that since my output was h of n in response to delta of n, and then due to delta n minus k, I have the response hn minus k, the output is also scaled by the same scalar. Why is that? You see, the reasoning behind is the principle of homogeneity, because my system is linear. So this is due to homogeneity principle, okay, or the principle of scaling. Um, you see, the idea behind is that if I have a zero input, if x of a is zero, the output cannot be non-zero. Output has to be zero, right? Similarly, if I scale the input by a certain scalar, the output is supposed to be scaled by the same scalar, right? It has to be amplified by the same scale. So that's linearity. That's one of the principle of linearity. The other principle of linearity that we discussed in the basic properties of systems was superposition. That is, now what I do is I superimpose um, all such impulses, shifted impulses. So I have x of k delta n minus k. Now what is happening is my summation, okay, my summation limits are over k now. So I'm summing up all the shifted impulses. Let's say in general, this happens from minus infinity to plus infinity. Then on the left hand side of the system, you see, you can interpret that this is an arbitrary sequence x of n. Since x of n can be decomposed into the unit impulse sequences, so this is my x of n, and this is indeed my x of n. So this is x of n that I've applied to an LTI discrete time system. Now see what happens with the output. The output, by the principle of superposition, will be the sum of all such responses. So this is my response to a shifted impulse of delta n minus k with the scale xk. Now if I have many such inputs which are summed up, the output is again the summation of all the individual responses. So the individual responses will be xk h of n minus k. So this output is precisely y of n. Okay, so the summation is again over k. In general, let's write this from minus infinity to plus infinity because that's how my input was. Okay, and this is my output y of n, and this sum is famous as the convolution sum or the superposition sum of the LTI system. So you note that in deriving this convolution sum, I had invoked the principle of time invariance, principle of homogeneity, principle of superposition, and that's how we have derived this. Okay, even if any one of this principle was not true, for example, if the system was time varying, then it won't be hn minus k. It would be some n minus n comma k. Okay, for time varying, for linear time varying systems, we would have the scaled sum responses, individual responses, because of linearity, but time invariance wouldn't hold. So this won't be n minus k. This will be some n minus k naught, let's say. Okay, so we don't know how many samples the output is delaying. The output is delayed by. It's not important to have the same delay by which the input is delayed for time varying systems, right? But if all these properties hold, then the output of an LTI system is always given by this convolution sum. Okay, so this is only valid for linear time invariant system. So now you see we have put together these two facts, linearity and time invariance, in deriving the convolution sum. Now the response of a linear system to x of n will be the superposition of the scaled responses of the system to each of the shifted impulses. So this is exactly what happened. Now we have this shifted impulses, okay, scaled, this is scaled shifted impulses, and these are this is not one, these are many such inputs which are summed up. So the output is the combination, the linear combination of the individual responses. The response to one impulse is h of n. H of n minus k is it's just the delayed version of the output of the impulse response. Okay, so it is already scaled by the same scalar by which the input is scaled, x of k. So it is the output. The output is a superposition. Then output is a superposition of the scaled responses of the system to each of these shifted impulses. Moreover, the property of time invariance tells us that the response of a time invariant system to the time shifted impulses are simply the time shifted versions of one another. Okay, so because of time invariance, the time shifted unit impulse are simply the time shifted versions of one another. So because of the time shift, we have the impulse response that is shifted in time by the same number of samples. Okay. Now the convolution sum representation for a discrete time system that are both linear and time invariant results from putting these two facts together. So time invariance and linearity, if you combine these two principles, you get the convolution sum. Okay. All right. Now, more specifically, consider the response of a linear but possibly time varying system to arbitrary input x of n. Okay. Any arbitrary x of n can be decomposed into a shifted scaled impulse sequence, okay, which we have seen previously. So we can still represent the input through the following equation as a linear combination of shifted impulses. Okay, so x of n is a linear combination of shifted impulses where x of k are the samples of x of n. Then let hk of n, this k is subscript, so let hk of n denotes the response of the linear system to the shifted unit impulse n minus k. Then from the superposition property for a linear system, from the following equation, the response y of n of a linear system to the input x of n is simply the weighted linear combination of these basic responses. So if you recall in the previous discussions on the basic properties of system, for example, if you have x of n, which is a linear combination of individual inputs x1, x2, x3, and they're scaled by the corresponding scalars a1, a2, a3. So you make a new input x of n, which is a linear combination of other inputs x1, x2, x3. Okay. With arbitrary scalars a1, a2, a3, the output due to linearity of the system will be the response, the individual response scaled by the same scalar and sum of it, okay, sum of all the individual responses. That's linearity. This is basically the principle of superposition. So for x2 you have the response y2, which is scaled by a2, so the output is also scaled by a2. Similarly, the output is scaled by a3, for which the input was x3 and the output is y3. Okay, so this is linearity. So y of n in general is the same scalar, will consist of same scalar and the sum of all the impulse responses. Because so what we considered was that even if the system is time varying, the system is going to have some sort of an impulse response. Okay, it is going to respond to an impulse, and that impulse response is hk of n. So hk of n is denoting the response of the linear system. It doesn't say time invariant. It says it's the response of the linear system to the shifted unit impulse delta n minus k. So the output is going to be, again by linearity, will be superposition of all such individual scaled impulse responses. These are the scaled impulse responses. This is from the principle of linearity. Okay, so this still holds for a time varying systems, right? So superposition and homogeneity holds. For example, over here, if x of k is 0, your y you see y of n becomes 0, right? So for 0 input leads to 0 output. This is the homogeneity principle of linear systems. So thus, according to the above equation, this is above equations, we know that the response of the linear system to the set of shifted impulses, unit impulses, we can construct the response to an arbitrary input. Okay, it's just the sum of all the individual responses, scaled individual responses. So interpretation of this result is shown in 2.2. Now, okay, what is happening here is we have a signal x of n as applied to an input to a linear system whose impulse response for h minus 1, h naught, and h1 to the signals delta n plus 1, delta n minus 1 respectively are depicted in figure 2.2b. So we have this arbitrary input x of n, okay, applied to a linear system, for which the impulse response, okay, now this is different. Okay, this is x of n, an arbitrary input sequence, but all we know is that we have the impulse response for delta n minus 1. Okay, this is the impulse response for delta n minus 1. Delta n minus 1 yields this response of an LTI system, linear system. Let me say the linear system. So for delta of n, my response is h naught of n. Then for delta n minus 1, this is my impulse response for delta n minus 1, h1 of n. Okay, and I have an input x of n, which again can be decomposed into these three shifted impulses. Okay, so x of n can be written as a linear combination of these shifted impulses. Superposition allows us to write the response of x of n. as a linear combination of the responses to the individual shifted impulses. Okay. Now what is happening? Let's have a look at figure 2.2c. This is the continuation of the same figure. Okay, I've shown. So we have shown in part A, which is x of n. Part B shows the response of the system. It is the impulse response of the system of a linear system. So we are looking at the graphical interpretation of the response of a discrete time linear system. So all we know is that when we apply delta of n, we have h naught of n. When we apply delta n minus 1, we have h minus 1 of n. When we apply, sorry, this is delta n plus 1. Okay. When we apply delta n plus 1, we have h minus 1 of n. When we apply delta n minus 1, we have h1 of n. So what is happening here is that now this is the decomposition. So on the right hand side, sorry, on the left hand side of this figure, left hand side of the figure, we have the decomposition of x of n. Okay, so this is the decomp. So if you add these three sequences, you get x of n. This will imply x of n. Similarly, what happens is now, since we know the response to delta n plus 1, to delta n plus 1, the system response is h minus 1n. And if we scale this by x minus 1 is this scalar, right? It's this scalar. So have a look over here. This scalar is negative, right? So what happens over here is this is going to make this sample negative, this negative, this will become positive. So this is going to come down like this, okay? And according to its weight, it goes like this, okay? This is going to come down like this. If we are going to scale this by x of minus 1, okay? So scaling this by x minus 1 on both sides, we know what is the response to delta n plus 1 of the system. Delta n plus 1 is h minus 1. So what we have done is we have simply scaled the delta n plus 1 by x minus 1. Okay, so this is basically my the sample x minus 1. So graphically what is happening over here is that my output is also scaled by x minus 1. Okay, similarly for x0, this is my sample of x of n at n equal to 0. And the output is to delta of n is precisely h naught of n. Okay, and this is shown over here, right? And this, if this is unity, then there won't be any difference to h naught of n. You can see over here it's pretty much the same. Okay, then we know what is the response of the system to delta n minus 1. That is h1 of n, and that is again, if the input is scaled by x1, the output is also scaled by x1, right? This is my x1. For example, if this is twice, then all these samples, for example, if you are going to multiply this with x of 1 over here, okay, this is going to go up like this. Okay, this the scale is going to be, it's going to be double. Okay, the weights are going to be multiplied by 2, for example, over here. So again, you have the picture like this. Okay, so what it means that if you have the response to the individual impulses, okay, so first against that you have h minus 1 for delta n, you have h naught for delta n minus 1. You know the response of the system is h1n. Now what you have done is, since you know the system is linear, you scale this by the individual scalars x minus 1, x naught, x1, and the outputs are also scaled by the corresponding scalars. Now, since the system is linear by principle of superposition, on the right hand side, if you add these three sequences on the right hand side, if you add these three sequences, what you obtain is the output y of n. This is corresponding to okay, this output y of n corresponds to a linear discrete time system, even if it is not time varying, not time invariant, time varying. The thing is that the system has some sort of an impulse response. Okay, but even for time varying system, the principle of, if it is linear, the principle of superposition and homogeneity still holds. So you have, if you add all these three sequences, adding them up will give you y of n like this. Okay, so this is by invoking the linearity of system. This is linear system. Okay, now the individual shifted and the scaled impulses that constitute x of n are illustrated on the left hand side of figure 2.2c. So we have seen this. the decomposition of x of n in terms of shifted impulses on the left hand side, while the responses of these component signals are pictured on the right hand side. Okay, so on the right hand side we have the responses of the system, scaled impulse responses of the system, right? So in figure 2.2d, we have depicted the actual input x of n, which is the sum of the components on the left hand side of 2.2c, right? So you see over here, we have this addition of these individual shifted weighted impulses that constitute x of n, right? So this is my input, and the output is y of n for a linear system. Okay, for a linear system. This is the linear system. But it's not important if it is time varying or time invariant. For linearity, the principle of superposition holds, right? So figure 2.2c is the actual output y of n, which by superposition is the sum of components on the right hand side of 2.2c. Thus, the response at time n of a linear system is simply the superposition of responses due to the input value at each point in time. So it's just the superposition of all the individual values, right? Now, in general, of course, the response hk of n need not to be related to each other for different values of k. However, if the linear system is also time invariant, now comes in picture the time invariance, then these responses to time shifted unit impulses are all time shifted versions of each other. Specifically, since delta n minus k is the time shifted version of delta n, the response hk of n is a time shifted version of h naught of n. So what it says is that if you have hk of n, which is the response to delta of n, then this subscript k, we can write this as, because you see over here, h naught of n was the response to delta of n, right? So then for any arbitrary shift of the impulse sequence, call it -1 or k equal to 1, delta n minus 1, delta n plus 1, the response is h minus 1, h1 of n. So this is, so the response at n equal to 0 is shifted to, let's say, n to k. So this can be written as h naught of n minus k, right? So if the linear system is also time invariant, then these responses, time shifted unit impulses, are all time shifted versions of each other. Specifically, since delta n minus k is a time shifted version of delta n, the response hk of n is a time shifted version of h naught. So what it says is delta of n, when delta of n is applied, the output was, you are calling this as h naught of n. Then if you apply to the same system delta n minus k, and the system is time invariant, okay, then what you have is an output in terms of h naught. In terms of h naught, the output becomes h naught n minus k. So this is exactly what this statement means, right? This means time invariance. So for notational convenience, we will drop the subscript h naught, okay, and define the impulse response, impulse sample response, as h of n. So h naught is my h of n, so you don't need to write the subscript. That is, h of n is the output of LTI system when delta n is the input. Then for an LTI system, the following equation becomes. So for this is precisely, okay, this is not exactly y of n. Y of n is this. This expression is y of n. Or okay, this y of n is okay. Okay, fine. This okay. This holds. So what this says is that for this expression is true for general linear systems, okay, but over here this becomes the response of the system is both linear and time invariant, okay, which means that, okay, you lose this subscript, and then you understand that the system is time invariant, so you will have the response to the shifted impulses as n minus k, h n minus k, okay. So this is linear. So if the transformation is such that the system is both linear and time invariant, then this is your output y of n, which is the famous convolution sum, or call it the superposition sum, okay. This is also a superposition sum, but this is for just a linear system. So superposition sum of the sequence x of n and h of n. Symbolically, this convolution operation is represented by an asterisk like this. Okay, and later on you will see that this convolution operation is also commutative, which means that you can write this as h of n convolved with x of n. What it means is that the order of convolution is not important. What is convolved with whom is not important. Okay, so this is also the same thing, and the proof is very simple. I mean, what you can do is, if you say that, okay, this is R. Okay, if R is my n minus k, and R is some dummy variable, it's also integer because n is integer, k is integer, difference is also an integer. That means k is equal to n minus R. So I'm just trying to prove the principle of, that I'm just trying to say that the convolution is commutative. Okay. So if this subscripts in for this subscript, the expression for y of n can be written as such. This becomes summation. Okay, since k is varying from minus infinity to plus infinity, R is also going to vary for the same range. So you have x of, for k I can write n minus R. Okay, and then I have on the right hand side h of R. So it doesn't matter. Okay, I mean, this could be n minus R, h of R. R can vary from minus infinity to plus infinity. You can even bring back k. Okay, you can bring back k, and you can write the expression as this expression is also, this is also the same thing. This is again y of n. This can be xn minus k, h of k. Okay, it's not important. H of n convolved with x of n, or xn convolved with h of n. The result is the same as y of n. Okay, so the convolution is commutative as well. Symbolically, in literature, this is denoted by an asterisk.